This is the third and final lecture on the subject of measurement for a Physics 11 course based on the Ontario curriculum. By now, we have covered how to make direct measurements with analog and digital devices. It is time to see how to use these measurements in calculations. However, in this first glimpse at the subject, we will restrict ourselves to calculations involving addition, subtraction, multiplication, and division of pairs of independent quantities. For example, we will not deal with the square root of a measurement. The equation that will be presented will only be valid for independent measurements. Those involve quantities for which the fluctuations within their range are not connected. For example, if quantity A takes up a value in the lower half of its range, it is independent from quantity B if it does not force quantity B to also be measured in the lower half of its range. Quantity B can end up anywhere in its range regardless of where quantity A is in its range. Since measurements are essentially ranges of possible values, what we can calculate with them will also involve ranges of values. It means that calculated quantities will also be expressed with best estimates and errors. Let's start with how to evaluate the best estimates of calculated quantities. We will consider the pair of independent quantities A and B. If you add them, the best estimate of this sum is the sum of the best estimates of A and B. Similarly, the best estimate of the difference is the difference of the best estimates, and so on for the product and the division of two measurements. Hopefully this is not too surprising and does not require a demonstration to be accepted. Basically, the best estimates of calculated quantities are obtained by using the best estimates of the measurements in the calculations. Now on to the task of evaluating the errors of calculated quantities. We will start with addition and subtraction. Let us call C the quantity that is the result of either the sum or the difference of two independent measurements A and B. The error on C is the square root of the sum of the square of the measurement error of A and the square of the measurement error of B. I do not intend to derive this formula. It involves calculus and probability theory, subjects that are usually not covered at a grade 11 level. But using the formula is not beyond a grade 11 level, and it is very useful in writing laboratory reports. After all, errors on calculated quantities are often needed to draw a conclusion about whether a predicted theoretical value is included or not in the range of its calculated experimental quantity. Now let us have a closer look at what is involved in this formula. It has a sum of squares that will always be greater than any of the individual terms in the sum. In particular, it will be larger than the largest term in the sum. This means that the error on C is never smaller than the largest measurement error involved in the calculation. To illustrate the use of the previous formulas, we will calculate the mass of the water only from the measurements of the mass of the bowl with the water in it, 242 grams, plus and minus 3 grams, and the measurement of the mass of the empty bowl, 36.5 grams, plus and minus 0.5 gram. The best estimate of the mass of the water only is then the best estimate of the mass of the bowl with the water in it, minus the best estimate of the mass of the empty bowl. The error on the mass of the water only is the square root of the sum of the square of the error on the mass of the container with water in it and the square of the error on the mass of the empty bowl. Using a calculator or a spreadsheet, we obtain 205.5 grams plus and minus 3.04138 grams. Note that the error in this expression is larger than the largest error involved, which was 3 grams. However, the rules about significant digits must be applied. Only one significant digit should be kept for the error, which makes it 3 grams. And the best estimate should be rounded to stop at the same decimal as its error, making the final expression for the calculated quantity be 206 grams plus and minus 3 grams. In the course that I taught, calculating errors was reserved for laboratory reports, but these lectures will eventually be about the theoretical aspect of physics, where calculation will involve best estimates only. However, the size of the error is still implicitly present in which decimal is used at the end of the best estimate. Since a sum or a difference always has an error at least as big as the largest error going into the calculation, the answer to those calculations should end on the same decimal as the term with the largest error. In the previous example, the 242 grams was associated with the biggest error because it ended one decimal place before the 36.5 gram measurement. The final answer, 206 gram, needs to end on the same decimal as the term in the calculation with the fewest decimal places. Saying that the final answer is 205.5 gram would be a mistake, because it would imply that this quantity is known more precisely than it really is. Let's move on to the task of evaluating the error of a product or ratio of measurements. The quantity D will be the result of either the product or the ratio of two independent measurements A and B. The error on D is slightly more complicated to calculate than the error on a sum or a difference of measurements, but there are some similarities. There is still a sum of squares, but the squares involve ratio of errors and best estimates. This ratio is called a relative error. It is sort of a percentage representing how big the error is in comparison to the best estimate. If we rewrite this formula a bit differently, it shows that the square of the relative error of the result is the sum of the squares of the relative errors of the measurements. The relative error of a product or a ratio of measurements is always greater than the relative error of each individual measurement. This means that the relative error of D is never smaller than the largest relative error of the measurements involved in the calculation. To illustrate the use of the previous formulas, we will calculate the area of a rectangle given the measurements of its length and width. The best estimate of the area is the product of the best estimate of the length times the best estimate of the width. To get the area on the area, you multiply the best estimate of the area with the square root of the sum of the square of the relative error of the length and the square of the relative error of the width. Using a calculator or a spreadsheet, you obtain 17,018 centimeters square plus and minus 1,158 centimeters square. Next, we need to apply the rules about significant digits. Only one significant digit is kept for the error, which makes it 1 times 10 to the 3 centimeters square, and the best estimate should be rounded to stop on the same decimal as its error. When you work with best estimates only, like with theoretical calculations, you can still assign the proper number of significant digits to the result of a product or ratio by recalling that its relative error is at least as big as the largest relative error of the measurements. Relative errors are related to the number of significant digits of the best estimate. The best estimate with the fewest number of significant digits has the largest relative error. For example, a best estimate of 1 kilogram has a relative error of roughly 100%, while 1.00 kilogram would have a relative error of roughly 1%. It means that the best estimate of the measurement with the lowest number of significant digits will dictate how many significant digits should be kept for the answer involving a product or a division of measurements. Let us revisit the previous example involving the area of a rectangle. The length is written with 3 significant digits, while the width has only 2 significant digits. Thus, it has the largest relative error. The final answer for the area should be written with 2 significant digits. Now let us look at the special case of a measurement multiplied by a constant. We can use the formulas mentioned previously by considering that a constant is a measurement with an error of 0. If we let quantity E be the product of a constant B with a measurement A, then the best estimate of E is B times the best estimate of A, and the error can be calculated using the formula for a product and using the fact that the error on B is 0. Taking the square root on both sides and remembering that an error is positive, we get that the error of a measurement multiplied by a constant is the absolute value of that constant multiplied by the error of the measurement. For example, you can apply this result to finding the diameter of a circle from the measurement of its radius. Both the best estimate of the radius and its error are multiplied by 2. We have just established that the error of a product of 2 times the measurement A is twice the error on A. But what about the error on A plus A? Is it the same as the error on 2A? If you use the propagation of error for a sum of 2 independent quantities, you get a different result, a smaller error. Which one is right? It turns out that the use of the error formula for a sum is not applicable here, because A is not independent compared to itself. The same problem will arise if you attempt to evaluate the error of a square of A with the error formula for a product. This concludes my series of 3 lectures about measurements, which had led to the concept of significant digits. The next step is to start the theoretical aspect of this course. Since mathematics plays an important role in physics, we will go over the concepts behind 2 very special types of quantities and the notation used to describe them. The next installment will be about scalars and vectors.